A very good afternoon to all of you.
Good afternoon, sir.
So as you can see, in this particular session, we have to mainly cover the first two units of block 4. And the first unit is simultaneous differential equations. And the second, that is unit number 15 in block 4, that is total differential equations. So these two we discussed today. So let us move to discuss about the first one, that is simultaneous differential equation. In our previous counseling session, we have discussed about the differential equations of first order, second order, and higher order. Also, we have discussed about the solution procedure to solve a first order differential equation, second order differential equation by using different procedure. So today we're going to discuss about the simultaneous differential equation. That means how they looks like, how can represent in the form of a simultaneous differential equation, and then the solution procedure of this kind of simultaneous differential equation. So let us move to define or look at the definition of simultaneous differential equation. So here again let us look at the outline of this particular unit number 14, that is all about the simultaneous differential equations. Here, first we're going to discuss about the representation of curves and surface in spaces. That means how mathematically we can represent by using equations and functions the representation of curves and surfaces in space, in three-dimensional space mainly. Now, then next we're going to discuss about the formation of simultaneous differential equation with the help of the equations of curves and surfaces in three-dimensional spaces. And then we're going to discuss about the solution procedure of this kind of differential equation dx by capital P, dy by q, and dz by r by using method of multipliers, one variable absent method. And finally, we're going to discuss about the applications, how can apply these basic ideas of simultaneous differential equation in the field of orthogonal trajectory system and particular motion in phase space, and third one is electric circuits. So now let us move to the page number 9 to discuss about the representation, how can represent equation of curve and surface in spaces mathematically. And as we know, in three-dimensional space we are using three coordinates, x coordinate, y coordinate, z coordinate. So very simply you can say that any surface of curve in three-dimensional space must have three variables x, y, and z. So these are some examples are given in picture. So look at that particular graph in figure number 2. That is a helix. So this circular helix, equation of circular helix has been defined here. So the equation will be in parametric form, and here the equation goes like that: x equals to a cos omega t, y equals to a sin omega t, and z equal to that was same, that is wt. So now these are the constant a, omega, and w. All are the constant. So look at the figure that was given in this particular phase, and that is a figure number 2. It is a circular helix. Now look at the lines that are drawn in dotted line. So these are all are the straight lines that are parallel to the z-axis, and that is the path of the circular helix that is started from a00, and we are moving in the form of increasing value of z, that is in the form of wt. So this circular helix can be represented by using parametric form, and the equation has been given here: x equals to a cos omega t, y equals to a sin omega t, and z equals to wt. And here t is the variable that will be from the interval minus infinity to infinity. So now let us move one other example. to define a definition of a sphere. So look at here. We know the Cartesian equation of sphere, that is x square plus y square plus z square equal to a square. Now that equation can be represented in terms of parametric form. So here we are assigning this kind of functions: x equals to phi t, y equals to psi t, and z equals to theta t. So in this way, that means we have to represent all the equations or all the variables present in the function in the form of a single parameter t to represent the equation of the space or surface in the space. Now let us move to the general definition. How can general define a
Sound is
function?
not clear.
Hello? Maybe your network will be problem. Network is will be there. So now let us look at that line. So a curve in space can be interpreted as the intersection of a surface and a plane, or surface and a surface also we can say. So curve means it is a path of intersection of two surfaces, or maybe a surface and a plane. So now look at the surface or equation of surface in space. This
Sound
equation,
is not clear, sir.
then
Sound
how
sound is
sound
clear. Sound is clear.
sound is
You see your system and the mobile. Okay.
now look at the equation. The equation is x plus by plus cz plus d equals to 0. So clearly this is the equation of plane in three dimension, and here we are using three variables x, y and z, and a, b, c, d all are the real constants we are using here. So generally this equation represents the equation of a plane, and that is a surface and three-dimensional space. And if you are going to represent in the form of, that means it can be converted now in the form of two variable form by assigning two arbitrary function, that is u and v, that is x equals to u and y equals to v, and we can represent here the same equation can be converted in the form of z, that means we can express in terms of z, and the expression will be in that form of minus of, that is au plus b v plus t all divided by c, but condition is that c may not be, must not be 0 here. Look at this expression here. The same equation is converted in the form of two parameters, and u and v are the two new parameters we are assigning here to represent the equation of the plane in surface. So that means according to our requirement, an equation can be designed by assigning some parameters. It may be t, it may be u, it may be v according to our requirement. So now look at one more example here. This is the equation of a sphere: x square plus y square plus z square equals to a square. Now the sphere can be represented parametric form by assigning two variables theta and phi. So here we have to remember that the value of x will be a sine theta cos phi, y equals to a sine theta sin phi, and z equals to a cos theta. And the theta will be defined in the interval of 0 to pi, and phi will be defined in the interval between 0 to 2 pi. And a is the radius of the sphere, that will be 0 to infinity, because radius cannot be negative, so that's why it will be in the form of 0 to infinity. That means according to our requirement, we can use desired parameters in the form of single or double to convert the function of three variable into two variable according to our requirement. So now these are the representation of curves and parameter and surfaces in three-dimensional system. So now this is the formal definition we are using in mathematics. So here the definition goes like that: if the Cartesian coordinates x, y, z of a three-dimensional space are connected by a single relation of this type, this function is represented in equation number 8, f of x, y, z equals to 0, and the collection of all such points covered by these functions is said to be surface, or the equation of surface in the space. Now again, the equation can be rewrite in the form of z equal to capital F of xy. Now, also otherwise, we can convert the functions in the form of two parameters u and v by assigning a new functions a new relation, that is x equals to phi uv and y equals to psi uv and z equals to theta uv. So we are assigning here, according to our requirement, we have to assign three functions phi, psi and theta in the form of two new parameters u and v, and here there must be an interval under which the function or the parameter u and v are bounded. So here u is bounded between u1 and u2 and v is bounded between v1 and v2. So we have to take care about that, the boundedness of these two parameters. And finally, also this is one of the another expression, that means u can be expressed in the form of capital F of xy and v also can be expressed in the form of capital F of xy. That means there are several ways to represent the equation of parameters and curves in three-dimensional space. We can design or define by using two parameters according to our requirement. So these are the some procedures. How can we convert these equations of three variable into two variable form? So now let us move to discuss about the main point of this particular expression here. So here we are going to move to the page number 12. And in the page number 12, we are going to discuss about the family of surface. Till now, we are looking or discussing about the equation of surface or curves. Now, if we have more equation of surfaces or curves, then how we can represent these? And these are called as family of surfaces. Let us see this expression. Is number 15. So let us first move to the idea. We are moving to discuss about the idea how we can represent a system of differential equation. So here, look at the equation number 23. So here, we have to assign in that form any differential equation. That means higher order differential equation can be converted into the system of differential equations in the following manner. So we have to assign here dx by dt equals to y and dy by dt equals to f. And similarly, these two relations combine together in the form of this proportional form, that is dx by y equals to dy by f equals to dt. So here y is a function of t. In the same process, we can also convert nth order differential equation in the form of this expression. That means nth derivative of x with respect to t can be represented by using a function like that. F is a function of t, x first derivative, second derivative, and n minus 1 the derivative of x in equation number 24. That means this idea can be now extended to represent a differential equation of nth order differential equation to a system of n first order differential equation. Please be concentrated in my sentence. So we are going to convert nth order differential equation to a system of n first order differential equation. So that means here we have exactly n numbers of first order differential equations will be there. The differential equation will be represented in that form dx by dt equal to y1, first equation dy1 by dt equal to y2, second equation. In that form, we are going to assign the last equation will be derivative of yn minus 1 by dt will be in the form of functions of x, t, y1 up to yn minus 1. So exactly these are n number of first order differential equation, and that has been developed from an nth order differential equation. So all together these equations are known as simultaneous differential equation of first order. So now let us move to discuss about the formulation. That means how we can develop or how we can form a system of differential equation from given equation of curve or surfaces in three-dimensional spaces. So now as we can see, here we have taken two family of curves. So here U is a family of curves that is in the form of x, y, z equals to C1, and V is also another equation of the surface that is x, y, z equals to C2. So here C1 and C2 are the any two parameters, and these are known as to family of surfaces, because whenever we are going to assign different values of C1 and C2, we will definitely get different equation of surfaces. So they are known as altogether known as two family of surfaces. Now whenever this type of equations are given and we have to form a system of differential equation, the process is quite similar or simple. So first we have to assign this total derivative of the first car or second car equal to 0. That means du equal to 0 and dv equals to 0. Total derivative of first car and total derivative of second car equals to 0. So here, as we know in the previous calculation, by using total differentiation process, we can represent partial derivative of u with respect to x, that means ux dx plus ui dy plus uz dz equals to 0. dv equals to 0, that means vx dx plus vy dy plus ez dz equals to 0. Now in equation number 29 and 30, as you can see clearly, we have two equations. Now we can solve these two equations for dx, dy and dz, and we obtain the following expression. So look at here. In this expression, we have a three fractions in the form of proportionality form. So here the dx divided by uy dz minus uz dy. So that can be directly obtained from these two equations by omitting the first two terms. So look at the denominator of the first fraction here, uy into vz minus vy into uz. So in this form, all other expression of dy and dz has been calculated for dx dy dz from these two equations 29 and 30. Now the denominator, for simple representation, to simplify our calculation, we have taken a new unknown function or new function, that is capital P in the form of xyz, the denominator of the first fraction, capital Q in the form of xyz function, the denominator of the second fraction, and capital R is the denominator of the third fraction. So this is the simple way we have to assign three known functions P, Q, R in the denominator of the first function, second function, and third function. So now here, as you can see in equation number 31, this equation, so this relation will develop a simultaneous differential equation of the two parameter family of curves in which the equations u equal to c1 and v equals to c2 are the solution to this system of differential equations. Now, the same has been discussed in example number 4 with this particular type of curve. So here we have taken two family of curves. First one is u equals to x square plus y square plus z square into c1, and second one is x plus z equals to c2. So clearly these are two family of surfaces. Now, according to the procedure to develop a differential equation or a system of differential equation, you have to first assign the total derivative of u equals to 0 and total derivative of v equals to also 0. Then we are adopting the same process of calculation, that means ux dx plus uy dy plus uz dz equals to 0. So now we are calculating ux means partial derivative with respect to x, that is 2x, partial derivative with respect to y, that is 2y, and partial derivative of u with respect to z will be 2z. These values are assigned here equals to 0. In the same way, we are using the values of vx and vz to represent the second equation in equation number 34. So now we are solving in the same manner that was discussed earlier in the general discussion of formation of system of differential equation. So here we are solving these two equations in the form of dx dy dz, and here the relation is in the form of proportional. So now this is the final relation that will give us a required system of differential equation of the given two family of curves. So this type of examples are given. So please go through each and every examples to better grip of this particular topic. Now we are moving to the methods of solutions of the differential equations or the system of differential equation in that particular form. So the differential equation discussed earlier in this session, that is dx by p, dy by q, and dz by r, is a system of differential equation that has been developed from two family of surfaces, or you can say that the curve of intersection of family of surfaces given in equation number 28. Now these are the two functions that is given u equals to c1 and v equals to c2, and how can we generate this relation that has been discussed earlier. So here again we write the value of capital P in the form of partial derivative with respect to u and v, and similarly in the other form of q, that means in the form of partial derivative of u and v, and similarly the other form of is r, partial derivative of u and v. The same formula or same relation has been used here to assign the value of capital P, capital Q, and capital R. So now let us see how can approach the solution procedure of this kind of system of differential equation. So now we are moving towards the general procedure to discuss about this kind of equations or system of differential equation. So let us discuss about the first example, and this example is an example number 6. So here the question is find the integral curves of the equations. So here the equation is given like that: dx by y square equals to dy by x square equals to dz by square y square z square. So here, look at the first two fractions in this relation. So first two fractions are clearly in the form of x and y, and easily we can separate the variables. So they are taken together, and by separating variables, we can solve easily to get the first solution in the form of x cube minus y cube equals to c1. And then we have taken the second and third fraction of the given relation or the system of differential equation. So here in the second and third fraction we have taken, so as you can see here, the denominator contains x square in second and third one, so it can be cancelled. After cancelling, we have represent dy equals to dz by y square z square. So now again by rearranging these terms, that means we have separate the variables y in one side and z in other sides. After separating variables, we have taken integration in both sides. After integration, we get another solution in the form of y cube plus 3 by z equals to c1. Now we have two solutions. First solution in the form of x cube minus y cube equals to c1 by choosing the first two fraction, and later on we are choosing the last two fraction to find the solution of the second type in the form of y cube plus 3 by z equals to c2. So these two relation together will gives us the solution to this system of differential equation. Or we can say that these are the integral curves given by the intersection of the family of surfaces x cube minus y cube equals to c1 and y cube plus 3y z equals to c2. So these are the simple procedure to solve a system of differential equation. By inspecting each and every term, we are choosing only or exactly two or three which are easier to solve by using integration process. So now let us move to discuss about the solution procedure of this kind of system of differential equation by using some multipliers. So that means now we're going to discuss how we can utilize some multipliers to solve this kind of differential equations. So again, we are visualizing here. That means whatever the general discussion has been discussed earlier in the session. That means we have taken two family of curves u equal to c1 and v equals to c2, and we have developed two parameter families of system of equations, and these are dx by p, dy by q, and dz by r. And already we have discussed about the values of capital P, capital Q, capital R, and the values of this capital P, capital Q, and capital R can be assigned by using the partial derivatives of u and v with respect to x, y, z. Now let us move to the next calculation procedure. So here you can see any curve of the family. That means again the first curve can be assigned to 0, total derivative du can be 0, and that can be represented like that: ux plus uy dy plus uz dz equals to 0. And similarly, from the second curve, we can assign vx dx plus vy dy plus vz dz equals to 0. So now, our job is to that we have to assign some functions p1, p1, r1 for the first curve and p2, q2, r2 for the second curve v in such a way that the value of p1 must be the first derivative of u with respect to x1, and q1 must be the derivative of u with respect to y. So that means these are the conditions in which we have to assign the values of p1, q1, r1 for the first curve and p2, q2, r2 for the second curve. And moreover, these two conditions must be satisfied that are listed in equation number 41 and 42. That means P into P1 plus Q into Q1 plus R into R1 must be equals to 0. And similarly, P into P2 plus Q into Q2 plus R into R1 equals to 0. That means if these two conditions 41 and 42 equations are satisfied, then we can say that yes, we can use these functions P1, P1, R1 and P2, Q2, R2 as a multipliers to solve the given system of differential equations. So now the given relation in the form of dx by p, dy by q, and dz by r has already given. So now we are using componendo dividendo rule, and we can represent along with multipliers. Q1 is a multiplier, Q1, R1 are the multipliers we are using here in the first fraction, second fraction, and third fraction. So here you can represent P1 dx plus Q1 dy plus R1 dz. Similarly, the same multiplier here we are using PP1 plus QP1 plus R1. In the same way, we can also use the other multipliers P2, Q2, and R2 in the first, second, and third fraction. And similarly, again we are using the componendo dividendo rule to represent this particular expression in the last fraction. And look at carefully the denominator that was written in the last two fraction are equating to 0, or the denominator must be 0 that was represented in equation number 41 and 42. If the denominator will be 0 in the last two fraction, then these two last fraction will be converted to very simple form, That means capital P1 into dx plus P1 into dy plus R1 dz equals to 0. Similarly, the second one also from the last this expression or the fraction, it will be converted to P2 dx plus Q2 dy plus R2 dz equals to 0.
सर
Yes.
सर जो यहाँ पे बोले कि मतलब 41 में सच दैट p into वो दोनों जो जीरो हुआ तो मतलब वो हो भी सकता है नहीं भी हो सकता
नहीं
है
नहीं, हो भी सकता है, नहीं हो सकता नहीं। हमें ऐसा चूज करना है जो P1 Q1 और R1 हमें फंक्शन चूज करना है। किसको देख के, पी क्यू आर जो दिया हुआ है क्वेश्चन में, उसको देख के हमें P1 Q1 R1 को चूज करना है। ऐसा वैल्यू, ऐसा फंक्शन चूज करना है जिससे कि ये दोनों रिलेशन को सेटिस्फाई करना ही है, तो उसी के हिसाब से आपको चूज करना है।
ओके सर
नहीं तो ये प्रोसीजर काम में नहीं आएगा। The total procedure, this total procedure depending only on these two equations 41 and 42. If they are satisfied, then we can move further.
ओके
Okay?
सर थैंक यू सर
Now, let us move to the next expression in 44, 45. As we have discussed here, after assigning this denominator equals to 0, the equation will convert it to simple form in the form of t1 dx plus t1 dy plus r1 dz equals to 0. And this equation has been developed from the relation du equals to 0, and the second has been developed from dv equals to 0. So once we get du equals to 0 and dv equals to 0, we can easily integrate these two equations to find out the surfaces u equals to c1 and v equals to c2. So this is the simple and general procedure to find out the solution of a system of differential equation by using multipliers. So now we are going to discuss the same in example number 8. That means how we can use these multipliers to solve this kind of differential equation. So here in example number 8, the equation is given like that: dx by nz minus ny equals to dz by nx minus lz equals to dz by L1 minus L1. That means in the same format, the equations are given: dx by p, dy by q, and dz by r. So here we first assign the value of capital P, Q, and R. So here we are taking P1, Q1, R1 and P2, Q2, R2. So these value we have to chosen very carefully and in such a manner that the relation must be satisfied in equation number 41 and 42, as it has been also established in this particular example. That is PP1 plus QP1 plus RR1 and PP2 plus QQ2 plus RR2 definitely equals to 0. Otherwise, we cannot move further. So here there is a small printing mistake here. P1 must be L and Q1 is M, then N, and P2 will be X, Y, and Z. So here that is L, M, and N. Then the relation will be 0. Then here X, Y, and Z, the relation will be 0. So now after assigning these to value by using this kind of this component or dependent of procedure, look at the expression here, the denominator is 0. So once you get the denominator 0, look at from the second or fourth, second last or fourth fraction, this fraction can be represented in the form of L dx plus n dy plus n dz equals to this particular terms can be represented together because here L, M, and N are constant, so that can be represented derivative of Lx plus My plus Nz, and now we can say that is equals to du. In the same process, we can also use for the second equation, that is here x dx, and that has been taken from the last fraction of the expression. So here in the last fraction we have x dx plus y dy plus z dz, and here as you can see x dx can be represented as the derivative of x square by 2, because if we are going to calculate the derivative of x square, that is 2x, and that will be cancel the denominator. So that can be represented x square by 2, y square by 2 plus z square by 2. And if we are calculating the derivative of all these three terms, the result will be x dx plus y dy plus z dz. And we are saying that it is dv. So once we get the expression in the total derivative form from the last second and last fraction of the given expression, now easily we can integrate to get a relation from the first total derivative form, that is du, and second one can be get from dv. So here the first one, that is lx plus my plus n equals to c1, and second one is x square plus y square plus z square equals to c2. So this is a simple and easy procedure to solve a system of differential equation by using multipliers. But here we have to keep in mind that whenever you are choosing the multipliers, we have to take care about the use of these multipliers P1, P1, R1 and P2, Q2, R2. In such a way that you have to choose this value such a way that the condition must be satisfied. Otherwise, it is not possible to represent in total derivative form. And again, if we cannot represent in total derivative form, then it is not possible to find out the solution of that kind of differential equation. So now, let us move towards page number 4. One variable absent. So here the equation or differential or simultaneous differential equation will be there, but if we observe the terms or fraction, if one variable is absent, then it can be solved in a particular process, and now we are going to discuss that one. So first we have discussed with the help of an example. So first example is given in the form of dx by xy dy by y square equals to dz by xyz minus 2x square. Now if we focus in this particular three fraction dx, dy and dz, in first two terms dx and dy, clearly we observe that z variable is absent. So that means these two terms taken together, and we can solve easily to find out a relation that will help us to find out the solution of this kind of simultaneous differential equations. So look at the first two fractions in the form of dx by xy equals to dy by y square. So here the expression is like that: dy by dx equals to f of x y, that is equals to y by x. That means if we represent y, one of the y can be cancelled in the denominator. So dy by dx can be represented in the form of y by x. So now, or we can use here the variable separable method to find out the solution of this differential equation dy by dx equals to y by x, and the relation of the solution will be x equals to c1y. That means this relation will help us to solve or to find the other solution of the system of differential equations. So here we are using the value of x equal to c1y in the last fraction, and that is here in the form of x square. It will be now c1 square y. So look at the expression from the last two fraction. We are assigning the value of x, and here it will be c1 square y square. So now y square can be taken common from the last fraction, and it can be cancelled with the denominator in the first fraction. Now after cancelling y square, we have a relation in terms of c1 dy equals to dz by z minus 2c1. So easily we can integrate this relation, and the first result in the left hand side will be in the form of y, and in the right hand side it is ln or ln z minus 2c1 plus c2. So finally we can assigning the value of c1y equals to x, because we have a relation x equals to c1y. So again we are substituting back the same variable x in place of c1y, and here this relation will gives us another solution or another curve. And here we have a two curve, that is x by y equals to c1 by choosing the first two fractions, and after choosing the last two fraction, another curve is x minus ln yz minus 2x plus ln y equals to c2. So these are the two family of surfaces which are the solution of the given system of differential equation. And the same process has been discussed in general prospect. So here the differential equation or the system of differential equation is dx by p, dy by q, and dz by r. And now here condition is that suppose the last two fraction does not have a variable x. So as you can see clearly, the last two expression does not have the variable x. So that's why we consider last two fractions and we represent in the form of dy by dz equals to functions of yz. And this first order differential equation in the form of z can be easily solved by using the process which I discussed earlier. Now, after solving this equation, we get a solution in the form of a function phi yz c1 equals to 0. Now, here c1 is any arbitrary constants. Now, similarly, we are assigning the value of any variable, it may be y or z, in the first two fraction to express the relation in the form of two variables x and y, because in the first two fraction x is the variable that was present in the first one but not present in the second one. That means from the relation of the solution in equation number 63 we have to substitute any one variable, it may be in the form of y or it may be in the form of z. After substituting the relation, we will get we able to get a relation in the form of dy by dx equals to z x y c1, and then we can easily, so clearly this is a first order differential equation in x, it can be easily solved. Now after solving, the relation will be in the form of a new function psi x y c1 and c2. So in this way, this is the general approach to solve a differential equation if one variable is absent. It may be x or it may be y or it may be z. So we have to check thoroughly which variable is missing. According to that one, we have to approach the process of calculation. So after discussing the one variable absent form, now we are moving to the applications of this idea which are discussed in this session. That means how we can utilize the system of differential equation in some applications of orthogonal trajectories of a system of curve on a given surfaces. So look at the figure in figure number 6. So here the equation is x square plus y square equals to z square into tan square alpha. So clearly this is a surface given by a, a plane is a curve. So here if we focus in that particular figure, look at these are the intersection of two family of surfaces. So all the blue lines may be considered as a one family of surfaces, and all the pink lines will be considered as a system of or family of another surfaces. So here the surfaces has been represented in the form of capital F equals to C1, one parameter family of surfaces, and another parameter family of surfaces has been given capital G equals to C2. And here we can clearly see the intersection of these two, one parameter family of surfaces of F equal to C1 and Z equals to C2. Now, and these two curves are known as now orthogonal trajectories because they are intersecting each other at 90 degrees. So that's why these are known as orthogonal trajectories to the family of surfaces. Now the same process we are adopting here. That means capital total derivative of f equals to 0 and total derivative of g equals to 0. That means df equals to 0 and dg equals to 0. And we are using the same process of calculation. We are after getting equation number 68 and 69. Again, we are using the solution process of dx, dy, and dz in the same manner that has been discussed earlier. In the denominator has been taken in the form of capital P, capital Q, and capital R. So now here in this figure, as you can see, dx, dy, dz. Suppose this is the expression of this kind of straight line that is a tangent to the curve, and dx dash, dy dash, and dz dash is another expression of this kind of straight line which is also a tangent to another curve, and both are intersecting at 90 degree. So that's why, so according to the values of p, q, and r, we have to consider another set of equations in the form of fx dx dash plus fy dy dash plus fz dz dash equals to 0. Now here we can see dx dash, dy dash, and dz dash are defined as the tangential direction of the orthogonal system at the point pxyz. So if we choose arbitrary at any point of the surface, that is xyz point, dx dash, dy dash, and dz dash will always define the tangential direction of the orthogonal system. And according to that particular tangential direction, we can define the equation, and that has been from equation number 17, that can be now modified in the form of p into dx dash plus q into dy dash plus r into dz dash. And again, from the relation or equation from 72 and 73, if we compare these two expressions in equation number 72 and 73, very easily we have this relation dx dash by p dash equals to dy dash equals to q dash and dz dash equals to r dash. Now look at the expression. This p dash will be clearly in the form of r into fy minus q fz. That means we now solve these two relations. Here we are solving this relation. That means equation number 72 and 73. From this equation we are solving for dx dash, dy dash, and dz dash. After solving this, we have the relation in the denominator, and the denominator has been taken in the form of p dash, q dash, and r dash. So after taking this kind of p dash, q dash, and r dash, we can now easily find out the solution of this particular equation number 75 to get the required orthogonal trajectories of the system. So let us discuss with the help of an example. So look at example number 13. So in example number 13, we have an equation in the form of x square plus y square equal to z square tan square alpha, and it's intersecting with a family of planes parallel to the line of the plane z equals to c. So here f is the first curve, g is the second curve. We are calculating partial derivative with respect to x, y, and z for the first curve f, and in the same second curve, that is gx, partial derivative with respect to x, y, and z has been calculated. Now we are using these values of capital F and capital G to calculate the values of capital P, capital Q, and capital R using the formula that has been discussed with the help of partial derivative of all the parameters f and z. Now, after calculating the value of p, q, r, again we are calculating the value of p dash, q dash, r dash, and again we are using the same formula that was discussed earlier in the general discussion. So here these are the values of p dash, q dash, and r dash. So after getting the values of p dash, q dash, and r dash, the orthogonal trajectories will be given by the relation dx by p dash, dy by q dash, and dz by r dash that has been obtained here. Now, the solution procedure will be exactly same. We have choosing first two fraction, and clearly in first two fraction, tan square alpha will be getting cancelled, minus 4 will be getting cancelled. Then we have a simple relation dx by x equals to dy by dy. And after integrating both sides, we have a relation x equals to c1y. So we are using here modulus symbol because the integration result will be logarithm, and logarithm is defined only over the positive numbers. So that's why finally, after removing the logarithm, we have a relation that is x equals to c1y you can represent. So now from the again we are using here the multipliers x in the first function, y in the second function, and after using multipliers x in the first function and y in the second function, that has been equating with the third fraction that is dz by minus 4x square plus y square. Here we are using multipliers to cancel the term x square plus y square in the denominator. So after cancelling these terms, and again minus 4 will be cancelled, then very easily we can calculate the derivative of x dx plus y dy equals to z tan square. So after integrating, we have a relation that is x square plus y square minus z square into tan square alpha equals to c2. So these are the simple process to solve a system of differential equation in the applications of orthogonal trajectory system. So after this applications, we are moving towards the next unit, that is in number 15, that is in page number 44. So let us move to the page number 44. So here in page number 44, here we could discuss about the total differential equations. So in formation of total differential equation, that means they are the outline how we can approach this particular unit in the form of in the formation of total differential equations, then the integrability approach to solve this kind of total differential equations, then method of integration process to solve this kind of differential equation by inspection, by variable separable, or by using the one variable separable form, or by using the homogeneous total differential equations. So let us move to discuss about the total differential equation. That means how the differential equations are look like, and in which form we can represent in the differential equation. So this is the formal definition. So formation of the total differential equation. That means from a given equation of curve, we can form a total differential equation. But condition is that it is possible to represent the given curve in total derivative form. In total derivative form. So let us see the general prospect has been discussed here. So here in equation number 2, there is the equation xy plus z square equals to c. X, y, z are variables, c is a parameter. And very clearly, if we are going to calculate the derivative of this expression or the equation, we will get y dx plus x dy plus 2z dz equals to 0. So now this expression, which is in the form of equation number 1. That means here it is the equation number 1 form. That means fx dx plus fy dy plus fz dz. So clearly this kind of equations are known as total differential equation, and that has been obtained from a one parameter family of curves. because here the given equation of the curve contains exactly one parameter or arbitrary constant. So that's why this kind of curves are known as one parameter family of curves, and we are obtaining the corresponding total differential equations in the form of equation number 3. So now look at the general aspect of this expression. So here in the form of equation number 4, we have a relation that is given f is a function of x, y, z equals to c, and clearly it is an one parameter family of surfaces. So again we are using the total derivative form here, df equals to 0. We are using fx dx plus fy dy plus fz dz equals to 0. So if the condition is imposed here, if fx, fy, fz have a common factor mu, and mu is a function of x, y, z, then you can represent the factor in the form of fx equal to mu into p, fy equals to mu into q, and fz equals to mu into r. And again we are saying that p, q, r are the functions of x, y, and z. So if this condition is satisfied, then the same equation can be modified in the form of capital P dx plus u dy plus r dz equals to 0. And this particular equation number 6 is known as the total differential equation in three variables x, y, and z. So let us quickly go through the example number 1 to discuss about the formulation of a total differential equation for a one parameter family of curves. So here, as you can see, a family of surfaces is given in the form of x, y equals to c into a minus z. So clearly it has been mentioned that c is a parameter, but a may be any constant. So that's why we will treat it as this is one parameter family of curves. And now it can be represented in the easier form of one parameter family of curve. Left hand side the expression other than the parameter c, in the right hand side only the parameter c will be there. Now, after expressing the given curve in this particular form, we are calculating the derivative in both sides. So, and then after derivating, we will get an expression of the result, and that particular result of the expression will be the required total differential equation of the given family of surfaces. So this is a very simple and easy approach to find out the total differential equation of an one parameter family of curves. So now let us move to discuss about the integrability of a total differential equation. So integrability approach can be done if it is possible to represent the differential equation in exact equation form. So the exact equation has been also discussed in the first order ordinary differential equation, but here we are using or discussing the partial differential equation. That means whenever it is possible to express the partial differential equation in its corresponding exact equation form, then integrability approach can be applied, and easily we can solve the equation. So here an example is given. Look at the equation number 7. It is x q y plus x q z plus z square y equals to c. So clearly this is a one parameter family of curves. Now after differentiating both sides, we will get a differential equation. Look at the expression in this last one. So this expression is clearly a total differential equation. Suppose this kind of total differential equation will gives, and in backward calculation, look at the backward calculation, this equation can be represented in the form of total derivative of x q y plus x q z plus z q y equals to 0. That means whenever a total differential equation is possible to represent in the form of exact equation, then we are using this integrability approach or integrable equation. So here easily we can integrate both sides to get the solution in the form of x q z plus x square y equals to c. So these are the integrability approach to solve a total differential equation. So here look at that theorem number one. So here a necessary and sufficient condition is defined, under which condition we can solve a total differential operation by using integrability process. So here if the total differential equation is given in the form of p dx plus q dy plus r dz equals to 0, then we can use it as a solution procedure by using integrability approach if this condition is satisfied. That means p all into qz minus ry plus q all into rx minus pz plus r into py minus qx. If this condition that was represented in equation number 10, if it has been satisfied, then we can say that yes, we can use integrability process as the solution of the total differential equation. So this is the necessary and sufficient condition to solve a total differential equation if the equation number 10 is satisfied, and that has been discussed in the following example. So please go through the examples to practice the calculation procedure to solve a total differential equation by using the integrability approach. So do you have any question till now? ऋतिका सिंह,
Yes, sir.
कुछ पूछना है?
No, sir.
तो आज के लिए इतना ही. Today we are going to end the session.
Okay, sir.
In the next session, we will discuss the rest of the units,
So,
16, 17, I think. Rest of the unit we will discuss later. So today we are going to end the session. So thanks for your joining.
thank you, sir.